So this is a short discussion on L'Hopital's rule. So this is a section 4.7. So there actually isn't really a lot to say to this. It's kind of an easy rule to apply. I don't say easier, but I think it's maybe one of the easier sections of the book. But that's actually a future term. I think it's easier than the optimization, which I think was maybe the hardest, if not one of the hardest, if not the hardest section of the book. Okay, so and so we've been talking about limits, and so we've learned all these different ways of taking limits or just rules about limits. So let's say C is like let's look at yeah. So one is direct substitution, right? That's one way of evaluating limit, and that might work, right? And then maybe you have a function, a limit in the form of C over zero, where C is itself not zero. Let's say C is some finite number, and C over zero will be plus or minus infinity. So here's this example right there: 4 over x minus 3 squared. So as x goes to 3, yeah, we get infinity. So yeah, because it's the numerator is positive and the denominator always be positive. So you get a larger and larger positive number as x gets close to 3. So let's say you have a function in the form, again, C is a some finite constant, and C over infinity, right? So that'll go to 0, right? So you take a number like 4 over x cubed. As x gets bigger and bigger, if the numerator stays constant, it gets closer and closer to 0. And you can graph that, right? And it approaches the line y equals 0. And then sometimes we've had limits in the form you get 0 over 0. So all our like the difference quotients for computing a derivative is 0 over 0. Yeah, and so like try algebra. Yeah, so for a lot of the derivatives that we did by hand, we were able to cancel out a term from the numerator and the denominator, and then evaluate the limit, where we didn't have 0 over 0 anymore. And then infinity over infinity. So for some functions, we can actually evaluate that limit for large values of x. So like here's this example here. So we just factor that x squared plus 5x minus 24 over x squared minus 9, and you factor that, and you eliminate the terms x minus 3 from the numerator and the denominator. And so so first of all, originally, if you just substitute x equals 3, I should have said that before, you get 0 over 0. So that's, oh my God, what do we do now? Okay, but yeah, you do some algebra, and you see that x squared plus 5x minus 24 over x squared minus 9 is equivalent to x plus 8 over x plus 3 when x is not equal to 3. And then you take the limit as x goes to 3, and then you get 11 over 6. Um, and so here's another example. Yeah, x squared minus 5. Now we're going to take the limit as x goes to infinity. And yeah, so now we look at these end behaviors. So for very large values of x, right? So now we're taking the limit as x goes to infinity of x squared plus 5x minus 24 divided by x squared minus 9. For very large values of x, that's about x squared. The x squared terms dominate, and the x to the first and the constant term, become trivial for very large values of x. So this function here, that quotient here, is about x squared over x, or you get a 1. Yes, the leading terms, so the degree of the numerator and the degree of the denominator are the same. So the limit as x goes to infinity is just the quotient of the coefficients. Okay, so that's all review. So now the exciting L'Hopital's rule. Maybe as exciting as that problem from 4.6 that I really liked. Okay, but you have to watch the video to know what I'm talking about. You have to watch the whole video. Okay, or you can just kind of scroll to the end. Okay, so we want to consider limits in the form where 0 over 0 or infinity over infinity. So these are called indeterminate forms. And so then we're not going to prove, the theorem is really not that easy to prove. And so we're going to use this rule. The limit as x goes to c. So first I have to say the conditions of the theorem. So let's suppose we're considering the limit of this quotient, or f of x over g of x, and we're considering the limit as x goes to c. So let's say the f of c, the limit as x goes to c of f of x is 0, and the limit as x goes to c of g of x is 0, or they're both infinity over infinity. What we can do is the limit in that situation, the limit as x goes to c of f of x over g of x is the limit as x goes to c of the derivative of f of x divided by the derivative of g of x. And often that makes it easier to calculate the derivatives. And then it's kind of noted right here. You're going to in Calc 2. So this is called indeterminate form, 0 over infinity. And we kind of learn more sophisticated ways of evaluating limits, like 1 to the infinity. What you'll learn is you'll take log of, you'll evaluate the log of the limit. But that's a coming attraction for Calc 2. And, or like 0 times infinity. Okay, so, well, 0 times infinity, that's, 1 over infinity is 0. So you just convert that 0 into 1 over infinity. So that one's not too bad. But we'll talk about that next semester with a different teacher, because I'm not teaching it or anything. This is my last semester. Okay, evaluate each limit. So and so here we get limit as x goes to infinity. So we're going to use, we know that the degree, so I'm talking about this problem right here, example 3, and we see that the degree of the numerator and the degree of the denominator are equal, x squared. And so we know that the limit is just the limit of the coefficients of the x squared terms. So the limit is 3 over 2. So that, you learned even in algebra, where you don't need, learn that like intermediate algebra. Okay, but now let's look at, now we're going to use the famous L'Hopital's rule to evaluate this limit. Okay, so of course, they're polynomials. And so the limit as x goes to infinity is infinity over infinity. Okay, so now you take the derivative of the numerator. Okay, so 3x squared plus 6x plus minus 1 goes to infinity. 5 plus 2x squared goes to infinity. Oh, let's take the limit of the derivative of f and the derivative of g. So you get 6x plus 6 over 4x. We still get infinity over infinity, but let's just, let's take the derivative one more time. And so you get 6 over 4, and that quotient is 3/2. You get the same limit. You better get the same limit, right? So the method of evaluating the limit, we shouldn't get different answers. If we are, something's very wrong. That wouldn't be very, that wouldn't be great. Okay, so here's another kind of fun problem. And so here we're taking, basically that is the definition of the derivative of 3 over x at x equal to 2. And now we're going to assume we already know we can take the, right, so this, you learned that earlier in the course. How can we find the derivative of 3 over x equals x equal to 2? So we evaluate this limit right here, 3 over x minus 3 over 2 divided by x minus 2. But let's use L'Hopital's rule. So as x goes to 2, you get 3/2 minus 3/2, get 0 in the numerator, 2 minus 2 in the denominator. Okay, well, the derivative of the denominator is just 1. Derivative of the numerator is minus 3 over x squared. Take the limit as x goes to 2, you get minus 3/4. Okay, so here's my cat. Yeah, she likes L'Hopital's rule. Okay, so let's take another one. So this one's not quite as a fun problem. At one time, tangent of 2x over 5x, we'd kind of go, oh my God, that's not a fun problem. And actually, you can convert that tangent to sine of 2x. We can turn that to a limit of, we could still do it. We just convert that tangent into sine over cosine, but let's use L'Hopital's rule. So the tangent of 0 is 0, right? Sine of 0 is 0, cosine of 0 is 1. So tangent of 0 is 0. 5x as x goes to 0 is clearly 0. Okay, so we have, so it's in the form, this indeterminate form, 0 over 0. Take the derivative of the numerator and the denominator. So we use, first of all, we have to use the chain, make sure you apply the chain rule correctly, or else you'll get the wrong answer. So the derivative of tangent of 2x is secant squared of 2x, and then you have to multiply by the derivative of the inside, 2x. So the derivative of the numerator is 2 secant squared of 2x. The derivative of 5x is just 5. Oh, now it's just 2 over 5. See how now this kind of maybe, oh my God, problem. It turns out to kind of relatively easy, as long as you know how to take the derivative of tangent of 2x. So, so here's another one. So I might look at this secant of, I think, no, I don't like this problem. Let's take the derivative of, as the limit goes to 0, of secant of x minus 1 over x squared. Oh, but now we've got L'Hopital's rule. And you think, okay, well, secant of 0 is, because it's 1 over cosine, we get secant of 0 is 1. So the numerator goes to 0, the denominator goes to 0, right? So let's try L'Hopital's rule. So the derivative of secant x minus 1, well, it's just secant of x tangent of x. The denominator is 2x. Okay, well, we still get that, we still get 0 over 0, right? Because the secant of 0 is 1, but tangent of x is 0. Of course, 2 times 0 is 0. Okay, let's try, we like L'Hopital's rule. We like taking derivatives. So let's just use the product rule to compute we're going to have to get basically the second derivative of secant, or we're going to take the derivative of secant, that numerator, secant of x times tangent of x. We'll use the product rule, right? We get secant of x times secant of x squared. And then the tangent of x times the derivative of secant of x. So, and so we get secant of x cubed in the numerator plus secant of x times tangent of x squared. And the derivative of 2x, see, we're not using the quotient rule, we're just taking the derivative of the numerator and derivative of the denominator. So the derivative of 2x is just 2. So now, here's our original problem. The limit as x goes to 0 of secant of x minus 1 over x squared. And the two applications of L'Hopital's rule gives us the limit as x goes to 0 of secant of x cubed plus secant of x times tangent of x squared over 2. Okay, so secant of x cubed, secant cubed of 0 is 1. Secant of x times tangent squared of 0 is 0. So we get 1 over 2. So that was kind of, I don't know, it's like, oh my God, I can do this problem now. L'Hopital's rule. Okay, so anyway, so the only bad news is the L'Hopital's rule maybe isn't always our friend, most of the time. Okay, but let's look at this fun problem right here. Or interesting. How about in general fun? Interesting. Okay, so students, we're going to take the limit as x goes to infinity, the square root of 2x plus 1 over the square root of x. Okay, the degrees of the numerator and the denominator are 1/2. So basically, we get the limit is the square root of 2 over the square root of 1. Right, so we my cat she doesn't want me giving this discussion. I like L'Hopital's rule, but I think my cat does. Okay, so but let's just try L'Hopital's rule. Okay, so this is the one thing about L'Hopital's rule. Some of us go crazy with L'Hopital's rule. First of all, make sure the conditions apply. Sometimes I see students using L'Hopital's rule and they haven't verified that the numerator and the denominator go to 0 over 0 or infinity over infinity. And sometimes they're using it inappropriate, when the conditions of the theorem don't apply, which means they're going to get the wrong answer. But sometimes, L'Hopital's rule, maybe makes the problem more difficult, or it doesn't ever give you an answer. Okay, so look at this one right here. We take the derivative of the numerator and we get 1 over the square root of 2x plus 1. We take the derivative of the denominator, like the derivative of the square root of x, right? Derivative of the square root of x is 1 over 2 square root of x. And then we just simplify that, right? We just, we simplify this. And so that turns into the square root of 2 times the square root of x over the square root of 2x plus 1. Okay, so once again, it's this indeterminate form. Oh, so let's try L'Hopital's rule again. We'll take the derivative of 2 times the square root of x over the derivative of the square root of 2x plus 1. And so the derivative of 2 square root of x is, you get this mess right here. 2 times 1/2 times 1 over the square root of x. The derivative of the denominator is 1/2 2x plus 1 to the negative 1/2 times 2 using the chain rule. Oh, it almost looks like we're back to the beginning. Yeah, it looks like, we get, and so the second application of L'Hopital's rule almost gives us, look, it's the original problem. So, we're in this infinite loop. So hopefully we recognize, if we're doing L'Hopital's rule, we recognize that we're back to the beginning and we don't keep applying L'Hopital's rule, because we'll be doing that the rest of our lives. So, so we realize, L'Hopital's rule doesn't really work. So we have to, that's the thing about mathematics. We have lots of tools, and sometimes we, one of our methods doesn't work. So let's go back to let's use some other method. Right. So for very large values of x, right, that plus 1 term isn't going to matter. It's the 2x dominates for super large values of like a trillion or a zillion. And so the square root of 2x plus 1 over the square root of x, it's really like near for super large values of x behaves like square root of 2x over square root of x. And so the limit is just the square root of 2. So L'Hopital's rule most of the time is great, but occasionally, maybe it's not always great. I mean, what I'm saying is just be careful. It doesn't always produce the answer that we're looking for. And that's it.